In this example, we're given a circuit that has already been transformed to the phasor domain. So everything we see are impedances, as you can see in here with the inductor and the capacitor. And what we're being asked to compute is this current in phasor form, specifically utilizing the Y-to-delta transformation. Of course, we can use any circuit analysis technique to find I, but we're being asked to specifically use Y-to-delta. And just as a quick reminder what the Wye-Delta transformation is, we have seen it in resistor form, so now we're talking about it in terms of impedances instead of resistances. It is exactly the same, but instead of using R's, we're using Z's, basically impedances. So here are the rules for if we want to transform from delta to Y. Pretty much we have Z1, Z2, Z3. These are the knowns. That's what you see on the right side of the equation in here. And the left side is what is unknown, ZA, ZB, and ZC. These are basically the Y. And we can do the same thing in terms of Y to delta. So the knowns will be ZA, B, and C. This is what you see on the right side here. And what we want is the Z1, Z2, Z3, and that's what you see in here. All right, so we can solve this particular exercise using either the Y to delta or delta to Y. So you can use, there's multiple ways to actually solve this circuit. You can use whichever you want. The one I'll probably use is I'll consider this form in here. Well, let me just highlight it that way. So this one here is pretty much a delta. So I can of course redraw this if you wanted to. And of course, if we redraw it, I could have redrawn it as an inductor in here, for example. Okay, so we have an inductor and we have the capacitor in here and we have the resistor. So that's a delta and we can transform it to a Y. So how do we transform this to a Y? Well, we will have somewhere some sort of a Z in here, okay, and another Z in here, okay, and another Z in here, and that will become a Y. So this is one approach to solving this circuit. So another approach to solving this circuit is the following. For example, instead of having starting with a delta, we can see, well, you know what, this is a Y. And we can transform this Y to its equivalent delta, and that equivalent delta will be something like this, for example. There will be a delta in here, and then another one here, and then another one here. Either of these approaches will do. Of course, there's multiple Y's. I could have basically showed you, well, here's a different Y, for example. This is a Y in here, okay? There's another delta, for example. I could have told you, like, hey, this here is a delta. Anyway, the way I'm going to do it is basically by converting the delta to a Y, this particular delta to a Y. Let me just show you here. So I will transform this, okay, to a Y, actually. Let me redraw it. All right, so I have redrawn that here, and I also copied the rule so that I don't have to remember it. So what I'm looking for is ZA. ZA is here. It's pretty much this multiplies by that. For our purposes, these will be the equivalent Z1 and Z2. All right, so let me just rewrite these. So ZA will be simply 40J times negative 15J divided by, well, I'll have to just sum them, which is 40J negative 15J plus 50 ohms, okay? And the same thing we can see with the ZB. Well, ZB is actually this one here in this our case, so that will become basically Z1 and Z3, which are the 40 and the 50 here. So we have 40J times 50 ohms divided by 40J plus negative 15J plus 50. Of course, the last one is ZC. That will be 50 times negative 15J divided by 40J negative 15J plus 50. All right, so let me just compute these, and let me redraw. Well, I'll compute them and I'll get back to you so that I don't waste your time. And here are the answers, and of course they're all in ohms because everything we have is impedances in ohms. Okay, so that's what we have. Now we can redraw that circuit now so that we incorporate the ZA, ZB, ZC, and of course, I mean, this will go away, this will go away, this will go away. We'll still have the 10 and the 40 ohms and the 14 ohms, of course. So I'm going to redraw that circuit. Okay, so I'll take the original in here and I'll just basically redraw that, and what I'll end up with is the following. So we'll have the source, Okay, it's 136 with 0 degrees. This is actually from here. Okay, let me just copy it and paste it down here. It will be helpful just so that I don't have to scroll up and down. Okay, and here. Okay, so we have that source, and then the 14 ohms stays in here. And now what we have is the ZA, which is right here. This is 9.6 minus 4.8J. And of course, if you think about it, the resistance is 9.6 and this is negative, so it's a capacitor. So this is capacitive reactance in here. This is inductive and this is capacitive. But anyway, we're just going to keep it as an impedance. Okay. And then we're going to say that this one here and this one here. Okay. So this would be the ZB, which is 16 plus 32J ohms. And this one here is -6, -12J. And what we're left with is, well, we can just keep it as a resistor or we can keep it as a box. It's fine. It's fine either way. So this is 40 ohms and this one here is 10 ohms. And now what we have to do is just combine things. So for example, these two here are in series, these two here are in series, and of course the results on both will be in parallel with that, and then in series with this, and then in series with that, and we will be able to figure out what this current here is. So let me just combine them. What I can tell you is the following. What we have is plus, minus, this is 136, 0, and this is in volts, of course. This is 14 ohms. Actually, let's keep it that way for now because we're going to combine all of them. So this one here, which is that box, will be simply 14 plus 9.6 negative 4.8J. Okay, so this is those two in series. Okay, and now what I'll have to do is I'll have to do these two in series and these two in series, and then the whole thing is in parallel. So I'll just tell you, well, there's a couple of things in parallel. The first one will be 10 minus 6 minus 12J. These two are in series in parallel with the 40 plus 16 plus 32J. Okay, and once we figure out what the result of all of these is, and I believe that will be 30 minus 16 of J ohms, we should be able to figure out what the current here is using Ohm's law in the phasor domain. So Ohm's law in the phasor domain tells me simply that if you want I, what you need to do is you need to do V divided by the Z equivalent. This is the Z equivalent that we have in here, and that will be 136, the angle is 0, 30 minus 16 of J ohms, and that will be equal to exactly, the answer will be 4, and the angle will be 28.07 degrees, and that is in amp. Of course, we can figure out what the actual I of t is, and that I of t will be simply 4 cosine, I don't know what omega because it wasn't given to us, so we'll have to write it as omega t, and then of course the angle will be plus 28.07 degrees, and that's in amp. And I'm assuming this is in cosine because it could have been sine depending on how it was originally transformed in here, but convention says let's use cosine, so I'm going to assume that this is actually cosine of 136 of cosine omega t. If it was sine, all I have to do is just write this in terms of sine. And that is the final answer. I encourage you to actually try it with different transformation, for example, using the ones that I've showed you at the beginning of this video.